Good morning. Today we'll be talking about arithmetic series. Now, a lot of times, since sequence and series sound so similar, and because Mr. P's brain always doesn't work quite right, sometimes I'll mix the two up. So hopefully I don't screw anyone up through the video or any discussion I have afterwards. They're two completely different things. They just sound very, very similar, and they work together hand in hand, which makes them even trickier. So let's start at the top. What is a sequence? That's review from yesterday's lesson. A sequence is a pattern of numbers. Now, an arithmetic sequence, which is our focus from lesson 1, was a pattern of numbers where we add or subtract between terms. So those are our two buzzwords from yesterday, sequence and arithmetic sequence. So today we're going to talk about arithmetic series. So we need to be able to define series. And then we'll talk about what an arithmetic series would be. So a series is the sum of all numbers in a sequence. Through the first half of the chapter, we're only going to be talking about series that have starting points and ending points. So add up the first 5 terms, or add up the first 15 terms. There are instances where it's possible to add all values in a series, but we're not going to talk about that until later in the chapter. An arithmetic series is then the sum of all numbers in an arithmetic sequence. For instance, if we had a number pattern, let's say 2, 4, 6, 8, 10, 12. This gives us a +2 pattern, so it's an arithmetic sequence. Now, if I wanted to find the series of these numbers from A1 to A1, 2, 3, 4, 5, 6, I'm going to add them up. 2 plus 4 plus 6 plus 8 plus 10 plus 12. 2 plus 4 is 6, plus 6 is 12, plus 8 is 20, plus 10 is 30, plus 12 is 42. Now, it doesn't seem like a very big deal to be able to create a series when you have a sequence from this example. But sometimes you need to add a lot of numbers together, like say 25 or 26 numbers. Is it still possible to find the series from the sequence? Just draw it out and add them all up? Absolutely. It's absolutely still possible, and I have some students do it. Some people over the years choose not to use the formulas, and they write out their sequences and their series to try to figure out what the answers are from start to finish. Now, when we get to geometric sequence and series, which is the next 2 lessons, when we're multiplying between terms, it'll be much more difficult than when we're adding between terms. Adding between terms isn't as big a deal. The more terms you have, the more difficult it'll be and more time consuming it'll be, but that's your choice. But now knowing that it can get a little tricky, we have a formula from yesterday to find our sequence pattern, to find any number in the sequence we want. So why not create a formula to find the series of the numbers? And that formula is S sub n equals n over 2 times a1 plus an. Now I want to talk out everything that's going on in this. S sub n represents the series. For 9 out of 10 cases, this is just the answer. There are probably a couple of tricky problems dashed in where they actually give you what the series is and ask you to find something else. But most of the time, that's just your answer. This n up here is the number of terms you're going to count. In my example earlier, I had A1 to A6, so there were 6 terms. 6 different things that I added up. And that 6 would go here. A1 is your first term, and AN is the last term. So if we go back to my example, 2, 4, 6, 8, 10, 12, and now we look at it again in terms of the formula. 2 is my first term, that is A1. 12 is my last term, that is AN. N is the number of terms, and we already said that's 1, 2, 3, 4, 5, 6. Oh, 6 over 2. So when we go to find our series, we have 6 over 2, which is 3, times 2 plus 12, which is 14. So that gives us 3 times 14, excuse me, which is 42. The exact same thing that we got when we added them up by hand. So, what should work? Formula should work, right? Now, there's 2 different cases throughout the homework when we're working with the series formula that you're going to see. Case 1 is when they just give you all the pieces. That's the easiest of the cases, and that means that there probably aren't very many of them, but they give us okay practice. Okay? Here's a good example of one that gives us all the pieces. A1 is 4, AN is 100, N is 25, and I'm looking for S sub n. So S sub n equals N 25 over 2 times A1 4 plus AN 100. I do 4 plus 100, which is 104. And I'm going to multiply that by 25 divided by 2, which is 12.5. I take my 12.5 times my 104, and I get 1,300. So what that's saying is if I took all the numbers from 4 to 100, with 25 iterates in between, so 25 steps, which means I think we're adding, I'm not really sure, I think we're adding 4s each time. So you'd have 4, 8, 12, 16, etc. And you added them all together, you would get 1,300 as your solution. That's case 1. Now if we come down into case 2 is when we're missing something. And I'll show you what I mean. So in my case 2 problem, I have S sub n equals, but I don't have n. n over 2 times a1, 132 plus 52. Without n or s of n, I can't complete this problem. But they do give me another piece of information so that I can, and that's d. d being -4 allows me to go find the information using the formula from yesterday's lesson. So yeah, you're gonna have to dig back into your notes from yesterday's lesson. You might want to put it right on the top of today's lesson. So yesterday's formula was an equals a1 plus n minus 1 times d. Now you'll notice that I have all the pieces except n in this formula, which is going to help me find n in this formula and allow me to find s of n ultimately. So let's go ahead and plug things in here. an is 52, a1 is 132, and d is -4. I'm going to step back and let people make sure that that's copied down for a second. I highly recommend that you always write out your series formula first. Find out if you have too many unknowns. See, I have 2 unknowns in this one, and then go to my sequence formula. So while you're looking at these, don't immediately jump to the conclusion that you won't have enough to do the series until you for sure know. And have your series written out so that it's ready to go when you're done looking for what you need to find. Because once we've found it, we can dump it back in. Alright, now when we're coming over here into our sequence formula, we need to be really careful how we move this stuff. These two things here are multiplied together. N minus 1 times -4. They cannot be broken right away. We have to treat this as if it's a variable, which it is. So we need to subtract away our 132 before we can mess around with this at all. Resist the temptation to try to do the 132 minus that 4. That can't work that way. Okay? So I have 52 minus 132, which I believe is 80. Yep, -80. Now I can divide off my -4. -80 divided by -4 will be 20. That equals n minus 1. Now here's where other people will make mistakes and slip up. They got their 20 and they thought, yes, done with the problem, right? 20 is going into n, I'm finished. But it's not 20 that goes into n. 20 is n minus 1. So we need to finish by adding that 1 over. It's actually 21 that's going into our n. So now I can come back to my original formula, and I can put that 21 into our formula right there. Now I have 132 plus 52, which is 184. I'm going to multiply that by 21 divided by 2, which is 10.5. And that's going to give me my S of n. 10.5 times 184 is 1932. When you're missing pieces and have to loop back into the sequence formula, it takes a little bit more time. But it isn't that much more difficult. Just slow down, take your time, put the pieces where they belong, and you'll be fine. We have one more thing we need to talk about yet. I'm gonna go ahead and get rid of this little chunk, but everything else I'm gonna leave. But because I did that, I'm gonna write that sequence formula up here, just in case somebody hasn't copied it down yet, to remind you to make sure to have it in your notes. The last thing we're gonna talk about is sigma notation. There's a couple of goofy problems at the end of the section that look like this. Now this symbol here is the Greek letter sigma, or it's an S. It's a Greek S, is what it is. And what it stands for, as far as mathematicians are concerned, is the sum of all values. In other words, sigma is a series. It's just a more compact way of writing a series out. So when mathematicians are writing big complex papers and they need to put sequences or series into them, they'll use sigmas to represent the series so that they don't have to write out the entire number pattern or give the number pattern a different purpose. They use a formula to draw out the number pattern. And so we're going to talk about how that works in reverse. You're not going to have to be able to create formulas from number patterns, just take number patterns out of formulas, which I know you can all do. Okay? So our first goal when we are working with sigmas is to write out our sequence. We're going to take every number between the number on the bottom and the number on the top, and we're going to plug them in here for n. So I'm going to make a little table, but we only really care about the stuff on the bottom. The numbers on the bottom are my actual sequence. The numbers on the top are just the values I'm plugging in to n down here. So first number that is going in is 1. When I put 1 in, I have 2 times 1, which is 2. The second number that's going in is 2. When I put 2 in, I have 2 times 2, which is 4. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. 6 times 2 is 12. 7 times 2 is 14. This pattern looks very similar to the one that I did earlier. It just goes one step further, doesn't it? So we know that when we added up the values 2 to 12, we had 42. Hopefully we can remember that. So when we add in 14, it should be 56. But now we're going to go in and find the answer to the sequence, and I'm going to use the formula to go ahead and do it just so that we're on top of that. Now, one of the trickiest things about using sigma patterns to find our series is sometimes the sigma patterns don't start at 1. In this case, we have the numbers from 1 to 7, and that is 1, 2, 3, 4, 5, 6, 7 values, and that's my n. If the sigma pattern starts at like 3 or 4 or 5, you need to count from this end to that end using your table to make sure you have the correct n value. Now our A1 is our first number in red down below. We don't care about the numbers up on top, those are just the numbers we plugged in. The numbers on the bottom represent our sequence. AN is 14. So we're going to do 2 plus 14, which is 16. Times 7 over 2, which is 3.5. So I do 3.5 times 16, which is 56, which is exactly what we said it would be. was able to do that. Now, I'm going to do a couple of example problems. Remember that our formula is S sub n equals n over 2 times a1 plus an. And our old formula was an equals a1 plus n minus 1 times d. Alright. These problems are directly from your homework, which is on page 660 if you would like to follow along. Problem number 16 gives us a1 is 7, an is 79, and n is 8. We'll start with our series formula, see if we have everything, and if we do, we'll just solve. If we don't, we'll go back to the sequence formula. S sub n equals n 8 over 2 times a1 7 plus an 79. 7 plus 79 is 86. 8 divided by 2 is 4. 4 times 86 is 344. And problem 16 is finished. The next problem I want to work on is problem 22. Problem 22 gives us a1 is 5, d is 1/2, and n is 13. So we're going to start with our series formula. S sub n equals n 13 over 2 times a1 5 plus, I don't know an. So now I'm going to have to go back to my sequence formula and find it. So an equals a1 5 plus n minus 1, 13 minus 1 times d, which is 1/2. Thirteen minus 1 is 12. 12 times 1/2 is 6. So an is 11. Now some of you may see that number and panic, but Mr. P didn't see that number and panic at all, because he knew that my common difference was 1/2. So my sequence is 5, 5 1/2, 6, 6 1/2, 7, 7 1/2, all the way up to 11, which is 13 steps. Totally made sense to me, but hopefully now it does to you as well. Now I know that an is 11, so I'm going to come in, take my an out, put 11 in. 13 divided by 2 is 6.5. 5 plus 11 is 16. 16 times 6.5 is 104. I'm going to do one more example from your homework. And that example is a sigma example. This is problem 34. Sigma k equals 7 up to 11, 42 minus 9k. So this tells us that we're going to plug in numbers from 7 to 11. So let's list them off here. 7, 8, 9, 10, 11. Make my table. We're going to go ahead and plug these numbers in. Now, 9 times 7 is 63. So when I put in 7, I have 42 minus 63, which is negative 21. Remember, you're plugging in the values here. So 42 minus 9 times 8, which is 72, is negative 30. 9 times 9 is 81. 42 minus 81 is negative 39. At this point in time, you could hit the pattern because you're going up by 9s if you catch it. 9 times 10 is 90, so 42 minus 90 is negative 48, which is 9 lower, I guess. You're going minus 9s away. And then 9 times 11 is 99, so 42 minus 99 is negative 57, which again is 9 from where we were before. Now remember, when we go to use our formula, we are using only the red values. S sub n equals n. 1, 2, 3, 4, 5 over 2. Don't forget that it is not 11 because we didn't start at 1. We don't have the numbers from 1 to 11 here. We only have the numbers from 7 to 11 here. So that is only 1, 2, 3, 4, 5 values. Also, resist the temptation to subtract. 11 minus 7 is not 5. Don't just subtract the top from the bottom to try to get the number of numbers that are there. Count them out from your table. Don't use shortcuts. Negative 21 plus negative 57. 5 divided by 2 is 2.5. Negative 21 and negative 57 is negative 78. Negative 78 times 2.5 is negative 195. So your total homework assignment for the day is on page 660, problem 16 through 34. And I gave you 16, 22, and 34. So I started and ended you, and then you're going to have to work out most of the middle. Hopefully it goes well.